All right, thank you for joining us today for part of CSIRO's AI monthly webinar series, Supercharging Simulations with AI using SmartSim. And today our presenter is Alessandro Ragazzi. Welcome. Thank you very much for joining us so early your time of the day. And before we get started, I'd like to acknowledge the traditional custodians of the land on which Pawsey is sitting here in Perth, Western Australia, and that's the Whadjuk people of the Noongar Nation. And I'd like to pay our respects to their elders, past, present, and emerging, and extend that acknowledgement and respect to all First Nations peoples in the room, on the call, and around the world. So thank you very much again for joining us. And without any further ado, over to you, Alessandro.
Yeah, thank you, Anne. So thanks everyone for having me. It's always a pleasure to collaborate with Pawsey. So let me jump to the next slide. So this is basically the agenda for today. So a couple of words about myself. So yeah, my name is Alessandro Ragazzi. I usually go by the name of Al in non-Italian speaking contexts. I am an AI and machine learning engineer at HPE. I am one of the lead developers and actually the top active developer of SmartSim. So I'm in charge with other people of the current features, but also of the future of SmartSim. So I'm always eager to get feedback on our infrastructure. And I have a mixed background. I have a PhD in computational science, and then I turned to AI once I joined Cray, and then, well, we were acquired by HP, and we brought the project into HP. So the structure of today's talk is, well, we'll start with a very quick intro about HPC, AI, and basically the origins of SmartSim. And then there are a couple of examples, so success stories from people who use SmartSim. First, it's an AI in the loop example. We'll go through these terms we coined in a couple of slides from now. This will be an example on oceanography. Then we have an example for AI around the loop, and that will be RELEXI, so it will be a reinforcement learning with CFD example. The next example will be just a quick overview of a full AI enhanced workflow using OpenMM. And then, yeah, we'll switch to some closing thoughts. So feel free at any time to interrupt me with questions or to type questions in the chat, which is monitored by Anne. All right. So let's start with HPC, AI, and SmartSim. So just a brief recap. I think by now everybody knows what machine learning is and what the types of machine learning are. But we always talk about supervised learning usually. Basically, what is supervised learning? Well, you have a model which has some free parameters, and you have some ground truth examples where you know the inputs and the outputs you would like to basically obtain when you pass the inputs to the model. You pass the samples enough times, or enough samples enough times to the model. You let it adapt its weights or its parameters, and then you have a trained model which can give you the best response to your inputs. People usually think about neural networks in this case, but think about just linear regression is like exactly supervised learning. You have one or few parameters and you want to tune them like with the samples you have. Obviously, artificial neural networks are the big thing nowadays. They apply a sequence of linear or nonlinear transformations with many, many free parameters. And then the challenge is that obviously that you have many free parameters. This means that you need a lot of data samples to constrain the problem. Another type of machine learning is reinforcement learning. So instead of prescribing what the output should be, you just prescribe something loose, like a reward for some actions taken by the model, the agent, which could have a neural network or could have other strategies. And in general, you just say there's a final goal or there are intermediate goals and there are rewards associated to these goals. but don't want to tell the agent how to achieve those goals. And the agent basically will act in a gamified environment, taking actions, influencing the environment, looking at the consequences, and taking the next action. And then there's unsupervised learning. In unsupervised learning, we don't know the answer. We don't know the desired outcome. We just know there is data and we would like to find relationships in the data. All these types of machine learning rely on data to learn, generalize, and make then predictions. So when it comes to combining AI with HPC, there are different levels at which AI can enter an HPC simulation. So the first thing is, if we look at the plot here, the graph here, we have the numerical simulation. That's basically usually your high-performance computing simulation running in parallel on a supercomputer. And now you have to decide where you want to put AI in the problem, because there are different levels. And we came up with this with these terms just to basically make sure that we understand where people want to use AI. So very close to the numerical simulation, there is what we call machine learning in the loop. So a numerical simulation usually has an algorithm where many steps are iterated over many times. And if at every step you apply some AI model to obtain a quantity or to obtain a byproduct of your simulation, then that's what we call machine learning in the loop. Then we have machine learning on the loop. And this is just like, you don't want to apply AI at every step. You want to apply every 1,000, 10,000 steps. Maybe you want some short simulations or some longer simulations to use them then to train a model or to perform inference. But then you have machine learning around the loop. And this really is the case in which you run the whole simulation, you collect the data, and you use it to train the model or use the data to perform any other type of AI inference. Farther from numerical simulation, we have edge AI. And the idea is like, your simulation is running on a supercomputer, on a system, and it's delivering results. You want to pick those results from another maybe system or another component of your gigantic workflow, pass them through an AI model, and take actions based on that. A typical example would be an alert system based on numerical weather predictions. So you have numerical weather predictions run on a supercomputer. You just get the output from another system, and you run AI on it, and you decide whether you want to trigger an alert. On the far right of this graph, we also have ML outside the loop, which is the case of intelligence sampling. That's a different approach. That's an approach where machine learning actually steers the simulation. It decides where the simulation should, so which kind of simulation should be run. Like, there are parameters in the simulation, maybe where do we want to explore the parameters, just because from the simulation, then it will extract samples for training. And so it wants to go in the areas of the simulation of the parameter space that are not well covered by its current state. So one question which usually arises is, why HPC and AI instead of talking about HPC versus AI, right? Against AI. So first of all, why not sticking just to HPC, to numerical models, right? Well, in general, numerical models are obviously well thought and well mathematically motivated, but sometimes, or maybe often, even in numerical models, you have free parameters. You have parameters you have to tune, just because maybe the model is abstracting the problem at some level where you don't actually have all the physics to compute, for example, all parameters. You want to get some parameters which are depending on a scale which is not captured by your numerical model, and then you just put a parameter that you can tune depending on the outcome you want. So in that case, we already know that the numerical model is not kind of perfect or perfectly thought. And those ad hoc models usually don't perform super well on a broad range of data. So instead of just using ad hoc models, we can use AI. But can we just then use AI, like only AI, right? Like replacing the whole numerical stack with just AI? Well, the short answer, at least for what we're concerned, is no. AI is currently limited by the data you basically use to train it. And so even if it will give good results on samples which are similar to what it was trained on, it will have a very hard time to extrapolate to parameter spaces it hasn't seen before, right? It has benefits, of course. An AI model can be run more quickly than traditional numerical models, and it's simpler. Like, it doesn't make a difference whether it comes from finance, biology, weather, or computational fluid dynamics. An AI model is always a model you put on your hardware, and then you pass inputs to it and you get the output. And basically you do everything in the toolkit you prefer, and there are no big changes whatsoever for any adaptation to a field. Whereas in numerics, we know that every field has its own toolkit, its own software, which has different resource constraints, different requirements in terms of infrastructure, of how you run it, how you pass inputs, outputs, and so on. So that's the difference, right? AI is basically kind of a one-fits-all solution. If you think about models, AI models, well, you in some cases, they are lower order representations of the true simulation. So what we mean, well, we see it on the right-hand side of this slide. On top, we see an AI surrogate model, basically computing, numerical weather prediction or climate simulations. And on the bottom, you see the ground truth computed with a numerical model, a very well-established numerical model. You really see that the one on top looks like a smoothened version of the one on the bottom, right? It captures the trends everywhere, but it doesn't really capture the high frequency details, so the pixel to pixel differences basically in this image. And that's exactly what we think of AI models as in many cases. They are low resolution versions of the numerical models. But there are downsides of AI models. Like, one is, once you have your AI model trained to solve a problem, how do you add now another level of complexity? Say that you had the model solving the problem at some scale. How now do you add another scale? Like, can you just do that by adding a part of the model as you would do in numerics, or do you have to retrain a new model from scratch? And obviously, yeah, the extrapolation is always very difficult. There are challenges to combining HPC and AI, which we think is the way to go in the future. Well, it is in the present already, I'd say. The first challenge is numerical. We won't talk about that much in this talk. So it's just, how can you characterize stability and accuracy of ML models, right? So for numerics, we have a lot of ways of determining stability of a numerical model. In ML, we are a bit behind in that. We just hope, many times we just hope it works as expected, or as we saw on some validation problems. We are more concerned with technical challenges to combining HPC and AI. We developed SmartSim exactly to solve a couple of these issues. First, numerical models, numerical simulations are usually written in Fortran, C, and C++, whereas machine learning, AI, data analytics stack is mostly based on Python. And the language divide between these two worlds is a big problem when you want to combine them. And then there's also an operational problem. How do you balance the cost of using GPUs for AI with code which is usually just CPU based? What do? You allocate a GPU for each CPU node you have, and then maybe waste a lot of GPU time because you are waiting for the CPU to produce the outcomes? Or do you allocate fewer GPUs, but then how do you send the data to the GPUs? These are problems we basically solve or find a solution for with SmartSim. And so this brings us to what SmartSim really is. So SmartSim, first of all, it's an open source library. It's always been an open source library, and it will always be open source. It's maintained by HP. It's my great pride to be a developer of SmartSim, but it's open source and everybody can contribute to it, let alone obviously download it and install it on a system. What it does, it provides a loose coupling, right, of like HPC and AI, but in general, loose coupling of any two applications. So the idea is to enable users to create workflows based on SmartSim by spinning up what we call an orchestrator, which is an in-memory database, which can be accessed by all entities in a workflow. So simulations can put data on the database and can get data from the database. So you can basically put together several simulations that all access the data on the database, or you can have other types of applications, like you can have visualization applications, which basically fetch the data from the database and visualize it, or you can have obviously AI models, either directly in the database because it's a database which has processing capabilities, or in other applications. So all of this happens with SmartSim, which basically creates this environment where applications know where the database is, and the database holds all the data. And the data never touches the file system. So everything is in memory. We don't write files as an exchange means between different applications. The data is always going from memory to memory, meaning that it's faster and it doesn't stress the file system for what it's basically not designed for. Okay, purpose of this slide is not to teach you how to write SmartSim code. It's just to show you how simple it is. So in general, what one has to do to make sure that, like, the application can use SmartSim is to instrument the code, the application code, with the client to SmartSim, which we call Smart Redis. It usually takes 10, maybe 20 lines of code to access all SmartSim functionalities from your code. So if you think about large code bases, which are, I don't know, 20,000 lines of code, adding 10 will not really make a difference in terms of complexity, but it will in terms of features and in terms of what you can achieve with your code. So on the top here, you see the lines we had to add to the oceanography example I'll be going through in the next section. Really just put the data on the database, run some AI on it, get the result back. That's all you have to do, and that's all you have to write. On the bottom, you see, I know it's possibly not readable, but the idea is just to show you how simple it was for us to run an ensemble. So an array of simulations of different instances of the same simulation instrumented with AI on a supercomputer, right? This is all we needed to write. It's a Python driver script because SmartSim's native language is Python. And that's all you need, right? Here you're defining your experiment, you're defining some parameters, and then you're just starting everything. We have example integrations. In CFD, we have many. We have integrations with OpenFOAM, Flexi, FASTA, libseed, and we're working on NACRS. We have examples with Weather, MOM6, NEMO, CSM. And we have examples with molecular dynamics, LAMPS, and OpenMM. And we are always open to developing a new integration if any user is interested in that. Okay, let's move to the first example. So it's using AI in the loop. So as I said, like, AI in the loop means very close to the simulation, part of the simulation itself. And this is an example. Well, this is the first study which used SmartSim, is a study which also drove the development of SmartSim. That's why SmartSim is so close to basically what what researchers would like to have when they work on AI, HPC and AI. It's because we developed it with HPC researchers at NCAR, the National Center for Atmospheric Research, just because they had some problems they wanted to solve. What was this problem? Well, they were using MOM6, and they still are, of course, a well-established Fortran code for oceanography. So this is a modular ocean model 6. The model obviously has different parts, different time steps, and different quantities which are computed. But one quantity which is kind of difficult to compute at some scales is the eddy kinetic energy. Why so? Well, if you have a fine grid, a very refined grid, then you can compute, you can resolve eddies and you can compute the eddy kinetic energy. But if your grid is coarse, basically it's a low resolution grid, then you don't resolve the eddies and you cannot compute the eddy kinetic energy, which is a foundational quantity of ocean models. And so basically low resolution models have this problem of not resolving eddies and not computing the eddy kinetic energy correctly. Before our study, the state of the art was just to use a prognostic equation with parameterized sources and sinks, and then use some length scale relations to convert the EKE to viscosity and other coefficients. But there were problems. The equation has terms that are tunable. So free terms, as I said, they're not super well motivated. It's always difficult to find the right parameters, and the model can induce errors, which may be even first order, which lead them to divergence of the prediction. What we proposed was an ML-based model, so ML-based solution. Instead of trying to add an ad hoc EKE model, let's just add machine learning. We trained a machine learning model on high resolution data so that it could compute the eddy kinetic energy for from large scale quantities. And then on the coarse grid, we ran the AI model as if it was on the high resolution grid. Right? So what we did was just to start SmartSim. SmartSim would kick off like the orchestrator, so the memory data store, and an ensemble simulation. So many instances of the same simulation, every instance just slightly perturbed in its initial values. And then every simulation would send its current state to the database, ask for an AI prediction, and get the result back. And we did this not for one, not for two, but for 12 ensemble members. So again, why not one simulation only? Well, we wanted to have some uncertainty quantification. We wanted to have statistical data about the simulation. And so we spun up 12 ensemble members on roughly basically 200 nodes. And the in-memory database was instead spun up on 60 nodes, each one having one single GPU. This was quite an old system. It was an XC50 system, so just one GPU per node. We ran inference, so we ran the inputs through the AI at each time step, but MOM6 has 3 different time steps, so 3 basically different time resolutions, and we ran it at the slowest time step, which is the one which computes basically, which is triggered every 3 hours of simulated time, obviously, which is like, I think 0.1 seconds in real time. Some numbers, after simulating 10 years, which took some days, we basically ran almost 1 trillion inferences, 1.6 million inferences per second. Inference was computed point-wise, basically. And the key results, well, we managed to offload the machine learning inference to dedicated nodes, right, which had like GPUs. So we sent the data to the GPU nodes, and then we got the results back. The neural network gave a more accurate prediction, like 20% better root mean squared error improvement compared to the state of the art. So here you see on the top the eddy resolving simulation. So you see that there is a lot of detail here. On the right-hand side, you see our prediction, or basically the average of our predictions. And on the bottom, you see what used to be the state of the art before our study. And as you can see, it misses a lot of the structure, especially in this area, which was the area of interest, and in these areas here, which were the areas of interest for the study. As you see, SmartSim at those latitudes is way more accurate than the prognostic state-of-the-art model. The overall performance decreased by 10%. But what do we mean by 10%? Well, we're comparing to just running one single simulation without AI. When we spun up 12 simulations at the same time, all using AI, all using just 16 GPUs, then the slowdown was 10%. But the improvement was so high that everybody was happy with this. Kind of a follow-up on this, again, MOM6, but this time the model was realized by the M-Square Lines organization with HP just to run it in this case. The study was published by Guillaumin and Zanna in 2021, and they trained a different type of model on different type of data, but again, just to resolve something that couldn't be resolved on that scale, so on that grid. It was embedded not at the largest step, but at a shorter time step, so the one which is kicked off every 900 seconds of simulated time. And we took that study and ran it on Frontier. Frontier, as you know, is the first exascale machine. It's at Oak Ridge in the US. We ran this study on 672 nodes on about 20,000 CPUs and 5,000 GPUs. Now, we actually flexed our muscles a bit here. We didn't really need 20,000 CPUs and we didn't need 5,000 GPUs, but we wanted to stress SmartSim and the whole infrastructure to see how well we performed and how well we scaled. And the key results, well, SmartSim scaled horizontally, and the cost was basically running the CNN, which was quite a complex model, and not in the communication. And here is the animation. As you can see, I'm no oceanographer, but I'd say that like western boundary currents are well resolved and were well depicted. So the MOM6 examples show this idea of AI in the loop, but AI was trained with data which we collected offline. So basically we ran simulations on high resolution grids, store the data, and used it to train the model. This is good, is a good approach if you know that then at production time, at runtime, where you will be using the AI model, the data it will see will be basically in the same ranges you had in your training samples, right? If your training samples didn't cover something that the AI model will see at production time, well, you may incur problems because there may be instabilities or unpredicted behavior of the model. And for this, we have a different example, which is AI around the loop. So around the loop, we mean basically that it takes whole simulations and use them to train a model. And this is, again, computational fluid dynamics, but at a different scale. And it's done with RELEXI, which is a different, more general purpose CFD tool. So we'll go through this animation later, but let's start with what the setting is. So the study analyzed two different CFD problems that can be posed as a reinforcement learning problem. And the study was performed by University of Stuttgart, HLRS, and HP. So the first problem is just to train a neural network to behave like a turbulence model. And I'll define what a turbulence model is in this context, and design and test an active flow control system. So the idea is, again, when you run a CFD simulation, the small scale is very costly, and resolving everything at the low scale, the small scale is very difficult or costly, actually. And so what you usually want to assume is that you can solve everything like taking a coarse solution and then adding an ad hoc turbulence model, which basically says, oh, based on what I see at the coarser level, the finer solution, the finer level solution should look like this. Now, there are different turbulence models, parameterized ones, but then people, obviously, when machine learning started being the thing in AI, in HPC, people started developing machine learning models to act as turbulence models. And they did it with the approach we just showed, right? To train the machine learning model, they would just collect a lot of data from simulations which had already been run, train the machine learning model, and then use it at production time or on new cases. That actually leads to instabilities and crashes, because in this case of basically high Reynolds numbers and highly turbulent flows, the machine learning model could be basically facing inputs that it's not been trained on. And these could lead to instabilities, which obviously, if they, for example, add energy to the system, then they result in divergence and catastrophic results. So what did the researchers do in this case? Well, they trained the model of turbulence in situ to ensure stability. I'll go through this later, but the idea is that while the simulation was running, they were training the model. The model was trying to predict the parameters to a turbulence model using this Smagorinsky coefficient, which is based on local velocity in the large eddy simulation. So the idea, again, you run a coarse version or a low filter version of your simulation and then try to extrapolate what's happening at the finer level. And the Smagorinsky coefficient more or less defines how the small scale subtracts energy from the large scale. And they trained a reinforcement learning agent on this. So where the reward function, like the gamified environment, was just based on how well it was predicting the turbulence, like the full spectrum result. The work was done by Kurz, Offenhäuser, and Beck. This is one of the publications, like the first publication I think they have for this work, but there are 3 different publications. I invite you to read all 3 of them because they're very interesting. They basically analyze different areas of the problem. So how did RELEXI, which is this reinforcement learning based on FLEXI approach, work? So SmartSim, or SmartSim IL, which means infrastructure library, was used to start the whole workflow. It started the orchestrator, again, the in-memory database, a reinforcement learning agent, which would be trained on this head node, basically, on the GPU node, and then some workers. Now, what do the workers do? The workers are those which run the simulation. So each worker node will take FLEXI, the CFD toolkit, and run a turbulence simulation at both low scale and high scale. And at each time step, they will put the result on the orchestrator, and the agent, so the reinforcement learning agent, will use its own policy to define the Smagorinsky parameter. So the Smagorinsky parameterization of the turbulence model, which it thinks it should be used in the simulation to better reflect the high, the low scale turbulence. The parameters will be used by the worker to predict the next step, and then the comparison between the real next step and the parameterized step will be the reward to the agent. And so in the end, we have what we call episodes, so small simulations run, right? And once the simulations are all done, the agent has enough experience, enough episodes to kick off the learning phase, like it will just train its own parameters on what it has seen in the simulation based on the actions it took. And once the parameters are updated, it will kick off new simulations using the parameters it computed so far. and from there, see if its parameterization is good for the new simulations. And by doing this loop, after a while, the agent parameterization and the simulation result converge, and they are basically stable. And at that point, one can be sure that at least there are more guarantees that the agent will be able to adapt to different settings in the simulation. Results, well, just quickly, the model converges in more or less 1 day, running on 8 CPU nodes and 1 GPU node. The energy spectrum was very well reproduced, at least up to the resolved wave numbers, which is K max here. It even showed some skills beyond the resolvable limit, and it showed generalizability to different Reynolds numbers. It incurred a 10% performance cost, but that's small compared to other approaches like implicit large eddy simulations. And obviously, one can define different reward functions to have different behaviors, to obtain different behaviors from the reinforcement learning model. So if you look, DNS, direct numerical simulation, is the green line here with the error shown as the green shadowing. And the yellow one is reinforcement learning model. So as you see, they're very close in the in this area of interest. But with the different reinforcement learning reward and agent, there was they could develop a different use case, and this is like the idea of reducing drag by controlling jets at the top of bottom of cylinder that inject momentum. So what do we mean? Well, we have here a parabolic profile injecting a flow into this domain, and there's an obstacle here. On top and on the bottom of this obstacle, they put some jets which can reduce or increase the momentum locally. And the idea is to reduce the drag, so to have a less turbulent flow after the object, so the obstacle is passed by the flow. And as you see, on the top, you see the uncontrolled version. And on the bottom, the reinforcement learning agents know how to basically add and reduce momentum here, and they can get a way better and less turbulent flow with reduced drag. They had like 5 probe points they were using to test drag. Okay, I'll now switch to the last workflow, which is a bioinformatics inspired one. So this is actually was a validation workflow for us. We didn't collaborate with other entities. We took a study, which is Gordon Bell Prize winner, Deep Drive MD. Basically, what's the gist of it? Well, the idea is always to compute the protein, the folded conformation of a protein. Like proteins are very long chains of atoms with a pretty complex 3D structure, which is not captured by basically the chemical formula. When you want to compute the 3D structure, the conformation of the protein, what you do, you run a molecular dynamic simulation. Takes basically discrete steps, tries to optimize the shape by minimizing the energy, add some random fluctuations so that you can try to get out of small local optima and so on. And the problem is that to fold the whole protein, it takes a lot. The simulations are very long, and many times you end up in local minima. Many times, different trajectories initialized with different random perturbations converge to the same suboptimal shape. So you cannot actually do a brute force approach where you try a lot of different random settings just to compute the conformation. You want to optimize this somehow. And this was exactly what they did in Deep Drive MD, and we reproduced with SmartSim. What we used was OpenMM, the Python API, TensorFlow, and scikit-learn, which is a Python toolkit for machine learning models. So let me just go quickly through what Deep Drive MD does and how we implement it. So you start with an unfolded protein. And instead of running the whole simulation, you just run short initial simulations starting from the unfolded protein or the partially folded protein in some cases. Then you store all the simulations you performed as all the steps you have encountered. And like the collection of steps is usually called a trajectory in this case, because it's a trajectory through the phase space of the problem. Then multiple neural networks, in this case, they are convolutional variational autoencoders, but let's just say neural networks, are trained on the discovered conformations. What do they have to predict is not the conformation itself. It's a low dimensional representation of the conformation. So basically, you can think of this as the shadow it would cast on a 2D surface or something like that. It's just a projection on a lower dimensional surface. Why so? Because we want to understand if the trajectories are clustered and they are converging to the same trajectory, or if they are going in divergent directions, which could be more interesting when we have to explore the phase space. So once we train the model, we use the best model we have trained. We trained lots of models at the same time, and then we use the best one to really compute this low dimensional representation of our steps. Once we have this low dimensional representation, we can cluster this low dimensional representation in the latent space, so in the projection space. And once we have the clusters, we can really say, oh, this bunch of trajectories all lead to the same best candidate. Let's just pick that one as one possible candidate. And then we find another cluster, we find the best candidate there, and then we find outliers, of course. And once we have all the new best candidates for our simulation, we re-trigger the molecular dynamics simulation. And we don't take anything from the file system anymore. The file system was just used for the input parameters, and then the rest is always in the in-memory database. Everything is just stored on the database, accessed on the database, and even the latent representation is computed in the database, so without moving the data anymore. Everything acts dynamically. It is not staged. Now I showed it in stages, but then it starts being dynamic where things are computed as soon as the data is available, which is different from the original approach. They then also improved the approach with a similar scheduling, let's say. And yeah, we basically were able to reproduce this very complex workflow all within SmartSim, all with this just one framework, and keeping the data in just one location, never writing to the file system. Okay, I think I'm a bit over time, but I'll just close the presentation. There are other ongoing projects using SmartSim for HPC and AI, notably OpenFOAM, all-purpose CFD toolkit. There are many research streams in that case. We have a collaboration to create an OpenFOAM model, which will use SmartSim natively. MFIX-EXA, another CFD toolkit, which is looking at training neural network surrogates for Lagrange and other solvers. MOM6, NEMO, CSM, again, oceanography. SmartSim is being used by most of the most well-established models in oceanography. And Simlint is part of the UK exascale, so Excalibur, the exascale funding initiative in the UK. It uses SmartSim again for performing AI operations in HPC simulations using what's called learned correction. Okay, in general, the takeaways. Oh, sorry. There is tension between AI for simulation and general AI. AI for simulation needs to be small because it needs to be performant. Otherwise, it will slow down the simulation. Numerical simulations are not usually tuned to map one input to one output, but more to map an input space to an output space. And there are new approaches in AI for doing this. For example, neural operators, Fourier operators also are useful in this case. The new paradigm is emerging in its workflows. So a scientific simulation is now only part of a larger, more complex workflow. So if you think about the past, we used to run large simulations on inputs, store the data, and then maybe visualize it. Now simulations are just one very specific part of a workflow, which then pass the result to the next phase of the workflow. The collaboration between domain and computer scientists is key to advancing science, right? The increasing complexity of computing and applications leads to the need for domain scientists and computer scientists to collaborate, because domain scientists are not experts, or often not experts in computing, and computer scientists or software engineers are not always aware of the requirements of domain scientists. And yeah, there's the real possibility for a virtuous cycle between research and industry in this case, because industry can introduce the technology and then research exercises the technology. Combining AI and HPC has the potential to make larger strides together. We have different ways of using AI. I guess the usages are actually limited by the researcher's creativity. And SmartSim we really think it's a library that helps lower the barriers to integrating AI and HPC. So whenever you want to mix AI and HPC, SmartSim gives you the possibility of exchanging data loosely without really thinking of, oh, how do I embed AI into my 20 or 30 years old code, right? You don't. You just pass the data out of the code and you get the results back. We're always open to collaboration, so please get in contact if interested. You have possibly seen that there was the Cray Labs email all the time here on the bottom, but like you can contact us there, or you can just download the SmartSim repo. It also has a Docker container with simple tutorials. SmartRedis is our client that allows the simulation basically to communicate with the database. There is a seminar we gave at NCAR about the first use case I showed, and there are many case studies always in our organization GitHub page. If you want to contact us not by mail but on Slack, just go to our repository and find there is a Slack invite you can click and you'll be added to the Slack workspace. If you go to the SmartSim repo, please start it so that you can always be updated with the new features of SmartSim. We are developing a ton of new features you'll be interested in seeing. And with this, I thank everybody who also contributed to this presentation, all of our collaborations at different institutions and companies. Yeah, I can open the floor for questions.
I have a question as well. So you were talking about AI around the loop and then AI in the loop, right?
Yep.
And the divergences and the unexpecteds that can come up. Would that not be applicable to anything? Because we can always come across unexpected things, right?
Yeah.
So how do you pick? Do you always pick for the divergent possibility?
Yeah, there are schemes to sample, to do intelligent sampling of your simulation. So to kick off the simulations where you know that your model is not converging or is not given the expected results. And that usually, obviously, just mitigates this problem, right? Obviously, if it's a static model and it's presented with data which is completely outside the training and outside any sample has ever been tuned on, the risk of divergence is always there. But if you try to go in those directions, usually smoothly enough so that your parameters do not explode, then you can try really to explore the space and find ways of mitigating that, adapting to new circumstances, basically.
Mm-hmm. Okay. Thanks.
Yeah.
Yes.
Thank you for the presentation. I'm just wondering, is the application of SmartSims only in the area of simulation, or can it be applied
Yeah, so in general, our paradigm is just that of coupling parts of the workflow together. We are actually also exploring the possibility, for example, of using SmartSim to connect sensors or experimental data collected in real time with other parts of a workflow, which could be AI or could be simulations. And we just usually talk about HPC and AI because it's what we developed SmartSim for, but SmartSim runs on a laptop, runs on a cluster, runs on a supercomputer the same way. And so we think that wherever you need AI and you don't, and just especially if you just need inference and you don't want to include, I don't know, TensorFlow or PyTorch calls directly into your code because they have some problems with dependencies usually, then yes, you can use SmartSim. Just the price you pay is obviously to spin up the orchestrator, but if it's local, usually it's just a process running on your laptop or on another node of your system or locally on the node where you're running the simulation. So that's not a big cost. And that enables AI to be used anywhere. Like it could be used also, yeah, in a data pipeline, for example. That's something we are exploring with some researchers right now. But we would be interested in having more use cases because if there's a divide between HPC and AI, there's also a divide usually between experimentalists and HPC to some level. Like it's you have to find the right contact point between the two worlds, which is then the source of fun usually. Yeah, I mean, the cases we're seeing are like field sensors, for example, in weather and stuff like that. So yes, they have ranges. Sometimes they gave results which are outside the ranges, and you have to cope with that. You have to put some robustness in your workflow in those cases. Yeah, that's clearly the issue. Then obviously, we are not dealing with maybe more complex types of sensors. Would love to do that. I would love to work with radio astronomy, for example, data. But yeah, for the moment being, we are just confined to weather and oceanography sensors, basically.
Yes?
When looking at the metadynamic simulations, have you guys applied SmartSim to metadynamic simulations?
Not yet. No, we are actively looking for a collaboration in that space. If you're interested in that, please get in touch with us because we would be happy to work on that, especially because of the new developments in that field, which are related to AI and machine learning.
In your presentation, you said that AI model is built on hardware, so I wasn't able to comprehend what that means.
Okay, so I think the thing is that sometimes I say that like the AI models have to be spin up on specific hardware. Is that the question?
Yep.
Okay, yeah. So, well, obviously AI models can run anywhere, but like because of the fast coevolution of AI and, for example, accelerators such as GPUs, then it's usually better to spin up the model where you have access to an accelerator, which can be, GPU in general, or it can be some dedicated types of FPGA or hardware. So the idea is always that if you're interested in maximizing the utilization of that, instead of like allocating a lot of those hardware accelerated nodes, you spin up the cluster on a bunch of nodes, and then you funnel all the calls from the simulation through SmartSim to those nodes, and that makes it basically hires the usage of your hardware, as it basically gets a lot of calls channeled to just fewer accelerators. So that's the idea. But obviously, if you have, and If you have a partition, for example, a partition system where you have CPU-only nodes and GPU-only nodes, then this makes a lot of sense because you want to maybe run the simulation on the CPU-only nodes and then the AI portion on the GPU nodes. And you don't want to allocate everything on GPU nodes because usually they are more expensive in terms of hours and in terms of project hours usually, and also in terms of energy consumption. So what you want to do is maybe run the simulation on CPU, and then the AI part, which can benefit a lot from accelerators, it's kicked off on the AI on the accelerated nodes.